This page introduces a really fundamental concept, the memory model. So, what is a memory model and why do we need one? Well, in a modern device, the processor isn't just connected to one big block of uniform memory. It has to communicate with lots of different things: main memory, RAM, peripherals like a USB controller or a display driver, and other system components. All these different parts live in the processor's address space, but they have very different characteristics and rules for how they should be accessed. The memory model is the set of rules that tells the processor how to interact correctly and efficiently with each part. The diagram gives us a simplified but very clear example of a memory map. Think of this map as a guide to all the addresses the processor can see. You can see it's divided into different regions. For example, at the top, we have peripherals. These are hardware devices. When the processor talks to a peripheral, it usually needs to read or write the exact, up to the millisecond value in a register. If it read an old, cached value, the system wouldn't work correctly. That's why this region is marked as uncached. The processor will always go directly to the hardware and bypass any caches. Next, we see the OS, or operating system, and the application space. This is all about security and protection. The OS is the core software running the whole system. If a normal application could accidentally or maliciously write over the OS memory, the entire system would crash. To prevent this, the OS memory region is marked for privileged access. Only the processor, when it's running in a special, trusted mode, like supervisor mode, can access this memory. Regular applications run in user access mode and are confined to their own application space, where they can't interfere with the OS or other applications. Finally, we have vectors. This refers to the exception vector table we talked about earlier. These are the instructions the CPU jumps to when an interrupt or exception occurs. The CPU needs to read these very quickly, but they almost never change. So, making this region cached, read-only is a perfect optimization. The data is kept in a fast cache for quick access, and marking it as read-only prevents it from being corrupted. So, for any given region of memory, the processor needs to know the rules. The slide breaks this down into 4 key things we can configure. First, access permissions. This is the core of the protection mechanism we just discussed. Who is allowed to touch this memory? Is it only for privileged code, or can user applications access it too? Second, read/write permissions. Even if you have access, what are you allowed to do? Can you only read the data, or can you write to it as well? This gives us finer control, like we saw with the read-only vector table. Third, memory types. This defines the fundamental nature of the memory region. Is it regular memory that behaves predictably, or is it a peripheral that might have side effects when you read or write to it? We'll dive into the specific types like normal and device on the next page. And lastly, caching/buffering and access ordering rules. This is all about balancing performance and correctness. Should we cache this region to speed up repeated accesses? And does the order of reads and writes matter? For regular memory, the processor might reorder operations to be more efficient, but for a hardware peripheral, you often need to perform steps in a strict sequence. The memory model lets us define these critical rules for each region. In essence, the memory model is what allows an ARM processor to manage a complex system securely and efficiently. Following on from the memory map we just saw, we need a way to tell the processor how it should interact with those different memory regions. In ARMv6 and ARMv7 architectures, this is done by assigning a type to each memory location. This type is essentially a set of rules for the processor. So, what does this type tell the processor? It defines 3 key behaviors. First, memory access ordering rules. Can the processor reorder read and write operations for better performance? For some types of memory, the order is critical, while for others, it's more flexible. Second is caching and buffering behavior. Should the processor be allowed to keep a copy of this memory location's data in its fast, local cache? Or maybe buffer a write operation to be completed later? And third is speculation. This is when the processor tries to be clever and read data from memory before it's even certain that the program will need it. This can speed things up, but it's not safe for all types of memory. Now, there are three fundamental, mutually exclusive memory types. A region of memory has to be one of these. First, we have normal memory. This is what you typically use for RAM, where your program code and data reside. For normal memory, the processor has the most freedom to reorder accesses, cache data, and perform speculation to maximize performance. Next is device memory. This type is used for peripherals, hardware components like timers, serial ports, or network controllers. When you access a device memory address, you're usually not just reading data. You're often triggering an action in the hardware. For example, reading from a status register. You need the absolute latest value from the device itself, not a stale copy from a cache. So, for device memory, the access rules are much stricter. Finally, there's strongly ordered memory. This is the most restrictive type. It ensures that every memory access happens in the exact order specified by the program. There's no reordering, no caching, and no speculative access. This is often used for older legacy hardware or very sensitive control registers where the exact sequence of operations is absolutely critical. To give developers more control, the normal and device types aren't just fixed settings. They allow for additional attributes. For example, you can specify the exact caching policy. And as the slide points out, you can configure a region of normal memory to be either cached or non-cached. This flexibility is key to building an efficient and reliable system. Why might you want non-cached normal memory? Perhaps for a specific data buffer that is shared directly with a DMA controller, to ensure both the CPU and the DMA controller always see the same version of the data.